Okay, so this ResNet paper, right? Even if image recognition isn't your thing, it's a pretty big deal. We're going to break down why.
Yeah, building really deep neural networks has always been like the ultimate goal. The deeper you go, the more powerful the network should be, right?
Yeah.
You can pick up all those subtle
More
patterns.
layers, more brain power. Makes sense.
You'd think so. But there's this thing, the degradation problem, that really tripped people up.
Degradation problem.
It means that as you add more layers, at some point, the network's performance just plateaus. And then, get this, it starts to get worse. Deeper networks doing a worse job, totally counterintuitive.
So adding more layers was actually backfiring. How's that even possible?
That was the million-dollar question. And it wasn't overfitting either. They showed that pretty clearly in the ResNet paper, ran experiments on those standard image data sets. It was an optimization problem, the way these really deep networks learn. It's just different. The old training methods couldn't handle it.
And that's where ResNet swoops in, I'm guessing.
Exactly. ResNet's all about residual learning. Instead of each layer learning some super complex function directly, it learns the residual, basically, the difference between what it wants to output and what it's getting as input.
So instead of the whole picture, it's learning the changes.
Right. And the key is, these residual functions, they tend to have smaller responses, which makes them a whole lot easier to learn, especially in these mega deep networks.
So how do they actually make the network learn these residuals?
Shortcut connections. Clever little things, really. These connections let information bypass one or more layers, creating a shortcut.
Like express lanes within the network.
Exactly. There are a few types, but the simplest one is the identity shortcut, which just takes the input of a block and adds it straight to the output. So the network can pass information through unchanged, if that works best.
And that helps with the degradation problem.
Think of it this way. By skipping layers, the network gets more flexible. No need to force every layer to learn some crazy transformation. If it's easier to just pass the information through unchanged, it can. This helps with those vanishing gradients and makes the whole learning process smoother.
So for us programmers, this is all super efficient, right? No added complexity.
You got it. Shortcut connections are super lean, no extra parameters, no increase in computational complexity. You're getting a more powerful network, basically for free.
Okay, so we've got the problem, deep networks falling apart. And we've got the solution, residual learning, with these shortcut connections.
Yeah.
What did their networks actually look like? What did they test?
They started with a pretty simple architecture based on VGG networks. Those were the top dogs back then. But even with this simple design, residual learning just shined.
So they built a plain network and then a ResNet version side by side for comparison.
Exactly. And the results were eye-opening. The plain network with 34 layers. Pretty high error rate, even worse than a smaller 18-layer version. Classic degradation problem. But add those shortcut connections, make it a ResNet, and bam! The 34-layer version crushed both the plain 34-layer and the 18-layer networks.
So ResNet let them go deeper and get better results.
Yeah.
Pretty impressive. But didn't you say they built some really, really deep networks too? Like hundreds of layers.
Oh yeah, they went all in, wanted to see how deep they could really go. But once you start hitting 50, 101, 152 layers, things get computationally expensive fast.
That's a lot of layers.
Right. So to handle these mega deep networks, they came up with the bottleneck design. It's a way to cut down on the number of calculations without hurting performance.
How does that work?
They use these one-by-one convolutions to shrink the data down before it goes through the main 3x3 convolutional layer. So bottleneck it, reduce the computational load, then another one-by-one convolution expands it back out.
Like compressing the data, doing the heavy lifting, then uncompressing it.
Perfect analogy. And here's the kicker. They lean hard on those identity shortcuts within the bottleneck design. Without them, the bottleneck would actually make things more complex. But with the shortcuts, the model size and computation time stay manageable, even with hundreds of layers.
So identity shortcuts, they're the real MVPs here. Okay, bottleneck design for the super deep ResNets. What kind of results did they actually get?
Hold on to your hats. They tested on a bunch of tasks, including the famous ImageNet dataset, and the results were, well, phenomenal. Way better accuracy than anything that came before, sometimes by a huge margin.
Blowing the competition out of the water.
Pretty much. They even tried a 1202-layer network on CFAR10 just because they could. That one didn't get the best performance, but it proved they had solved those deep network optimization problems.
So more of a look what we can do than a practical thing.
Exactly. ResNet wasn't just about breaking records. It was about changing the game. It opened up so many possibilities, and its impact goes way beyond image classification.
Okay, maybe we should talk about that impact next. How's ResNet being used in the real world?
Let's save that for part 2. It's pretty exciting stuff.
Sounds good. We'll be back after a quick break. All right, so before the break, ResNet's impact, right? How did this research actually change things in computer vision?
Well, one of the biggest things was in object detection. Before ResNet, people were mostly using those shallower networks, like VGG, as the backbone for their object detection systems.
Backbone meaning.
The core part of the network, the part that extracts features from the image. But with ResNet, they could use much deeper networks, like ResNet 101 as the backbone, and that led to some pretty big performance jumps.
So they just swapped out the old network with a ResNet, and boom, better results.
It was a game changer, really. On the COSIO dataset, that's like the standard benchmark for object detection, they saw a 6% increase in MAP at 0.5.95, which it's basically a measure of how well the system finds objects.
And that's a significant improvement,
Yeah.
6%.
Huge. Especially when you consider they only changed the network architecture, nothing else. It shows you the power of those deep features ResNet can learn.
And it wasn't just object detection, right? ResNet was used for image segmentation, too.
Mm-hmm.
Dividing an image into different regions based on what's in it.
Yep, and again, big improvements compared to the older networks. They even snagged first place in a bunch of categories at those big computer vision competitions, ILS, VRC, and COSIO 2015, ImageNet detection, localization, COSIO detection, and segmentation, the whole shebang.
So ResNet was like dominating, clearly a big deal.
Oh, absolutely. And it goes beyond just those tasks. ResNet's become like a fundamental building block for tons of computer vision applications. Facial recognition, self-driving cars, even analyzing medical images, you name it.
So if you're working with images, ResNet's something you got to know. But let's bring it back to our listener, the programmer who might not be a computer vision expert. Why should they care about all of this?
Well, on a basic level, ResNet shows how a simple, elegant idea can completely transform a field. Sometimes the best solutions are the ones that seem obvious in hindsight,
Like, why didn't we think of this before?
Exactly. But it also highlights how important it is to understand the problem you're trying to solve. The degradation problem had been around, but ResNet went deeper, figured out the why, and that's what led to this breakthrough.
So curiosity pays off. Good takeaway for any programmer.
For sure. And for programmers specifically interested in deep learning, well, ResNet gives you this amazing tool. Those shortcut connections, they're like a secret weapon for overcoming the limitations of the old ways of doing things.
So even if I'm not building an image recognition system, I can still use these ideas.
Absolutely. The principles behind ResNet, they're applicable across the board, whether you're dealing with natural language processing, time series data, anything really. Those shortcut connections can help you build deeper, more powerful networks.
So ResNet's not just about image recognition, it's about a whole new approach to deep learning.
Nailed it. And its influence is still felt today. People are still building on these ideas, finding new variations and uses for it.
So this paper, it's still relevant, even though it came out a while ago.
It's essential reading for anyone who wants to understand how deep learning got to where it is today. ResNet was a turning point.
Okay, so we've talked about the impact of ResNet and how it's used in practice, but this is the deep dive, so we like to go a little deeper. What are some of the, key takeaways from the paper itself?
You know what really impressed me? How thorough their experiments were. They didn't just test ResNet on 1 or 2 data sets. They went all out, testing it on all these different benchmarks to really show it worked.
So they were determined to prove this wasn't just some, lucky coincidence.
Exactly. They were super rigorous, and that's one of the reasons why ResNet has become so widely adopted.
And they also explored a bunch of different variations of the ResNet architecture, right?
Oh, yeah. Different depths, different types of shortcut connections, different block designs. They tried it all. They really wanted to understand the whole design space.
So it wasn't just, here's ResNet, we're done. They kept iterating, making it better.
Right. And that's another important lesson for programmers. Don't be afraid to experiment, try different approaches, see what works best for your problem.
Always be iterating. Always be learning.
Couldn't have said it better myself. And ResNet is a perfect example of how that approach can lead to amazing things.
Okay, so we've covered the impact, the key takeaways from the paper.
Yeah.
What's the big picture message? What does ResNet tell us about the future of deep learning?
I think ResNet showed us that we're just scratching the surface. Before ResNet, people were hitting this wall with vanishing gradients, the degradation problem. But ResNet smashed through that wall, opened up all these new possibilities.
So it's kind of like a revolution,
In a way, yeah. It changed the way we think about building and training deep networks. And it set the stage for even more powerful architectures that are being developed now.
So what's next? Where do we go from here?
That's the exciting part. Now we can tackle problems that were once thought to be impossible. Build systems that can understand images, videos, text, even human behavior with incredible accuracy.
It's a little bit scary, but also pretty amazing.
It is. And ResNet played a big part in getting us here.
So what's the one thing you want our listener to remember about ResNet?
That even a simple idea can make a huge difference. ResNet showed us that if you understand the problem and think outside the box, you can achieve incredible things.
And on that note, I think we've covered just about everything there is to say about ResNet.
I think so too. It's been a fun deep dive.
It has. And for our listener, if you're interested in learning more, go check out the ResNet paper yourself. There's a lot of great stuff in there we didn't have time to cover.
And don't be afraid to play around with these ideas, experiment. You might be surprised at what you can do.
Great advice. That's all the time we have for today. Thanks for joining us on the deep dive.
It's been my pleasure.
So we've talked about the impact, how it's being used, but let's zoom out for a sec. Our listener, the programmer who maybe isn't building the next big image recognition thing,
Yeah.
why should they care about this paper?
ResNet's like this perfect example, right? A simple idea, but it completely changes the game. Sometimes the best solutions, they seem so obvious once you see them.
They're like, wait, why didn't we think of that?
Exactly. But it took really understanding why deep networks were having these issues. Everyone knew about the degradation problem, but ResNet went further. They figured out the root cause, and that's where the real innovation is.
A lesson in problem solving there, for sure. But for someone writing code, what can they actually take away from this?
ResNet gives you this powerful tool, those shortcut connections. They're like cheat codes for building deep neural networks. Networks that can learn super complex patterns, but without all the optimization headaches.
So even if I'm not working on image recognition, those shortcuts are still useful.
Oh yeah, totally. The ideas behind ResNet, they apply anywhere you're using deep learning. Natural language processing, time series, anything. Shortcut connections can help you build deeper, more powerful networks, period.
So it's not just about images, it's a whole different way of thinking about deep learning architecture.
Exactly. And its influence is still huge. People are still building on the ideas from this paper, finding new ways to use them.
So even though it came out a while back, it's still relevant today.
Absolutely. If you're serious about understanding how we got to where we are with deep learning, this is essential reading. ResNet was a major turning point.
Okay, so we've talked about the impact, how it's used, the key takeaways from the paper itself. What's the big takeaway here? What does ResNet tell us about the future of deep learning?
I think ResNet showed us we were barely scratching the surface. Before this, everyone was running into that wall with vanishing gradients, the degradation problem. But ResNet just blew through it, and it opened up all these new possibilities.
It was like a revolution then.
Yeah, you could say that. It changed how we think about building and training deep networks. And it paved the way for even more powerful architectures that are being developed right now.
So what's next? Where do we go from here?
That's the best part. Now we can tackle problems that seemed impossible before. We can build systems that can understand images, videos, text, even human behavior, and do it with incredible accuracy.
It's kind of mind-blowing and maybe a little scary.
It is. And ResNet was a big part of getting us to this point.
So if there's one thing you want our listeners to take away from all this, what would it be?
Simple ideas can have a huge impact. ResNet showed us that if you really understand the problem and you think outside the box, you can achieve amazing things.
And on that note, I think we've pretty much covered ResNet.
Yeah, I think we hit all the main points.
This has been a really fun deep dive. Thanks for joining us. And for everyone listening, if you want to learn more, check out the paper yourself. Lots of great detail we didn't have time to get to.
And don't just read it. Play around with these ideas. Experiment. You might be surprised by what you discover.
That's what it's all about. Until next time, keep on diving deep, everybody.